Now that we talked about virtual memory in theory, I want to talk a little bit about virtual memory, how we can use it in practice. So for that, I want to give an example. The example I'm going to give, we're going to map a file into our virtual address space, and then we're going to use the fact that we've done that for I/O. Let me go ahead and start typing. Alright, so we're going to write a file called savearray.c. So C program. We're not using command line arguments for anything, but we are going to use a ton of header files. We're going to be doing some system calls. We're going to be doing some I/O type system calls. We want to be able to do error handling. We want to be able to print stuff. We want to be able to do normal standard lib things, and then the sort of key thing that we're going to be doing in this example comes in from the sysmn.h header, where we get a new system call that lets us do some fun stuff. Now, because we're doing system calls, I want to go ahead and write a helper function. Which is going to go ahead and check the return value from system calls. So if we get a -1, we're going to go ahead and use this p_error function to print out our actual error message. That'll help a lot in debugging. Hopefully we won't need to do any debugging and my sample code will work fine, but no bets. So what we're going to be doing is we're going to be storing an array of 10 integers in a file. This program is called saveArray, and so it's going to generate 10 integers and write them out to a file. To do that, first we're going to open a file called array.mem. Now, this file is going to be created if it doesn't exist. It's going to be truncated if it does exist, and then we're going to have read and write access to it. And if we do need to create it, it's going to have a file permissions of 0644, which is reasonable for a file that we aren't going to execute, but we may read and write. So we're going to assert that that wasn't an error. We're going to pass that this was the open call for the purpose of error messages. Now, next thing that we're going to do is we're going to truncate that file to this size. Now, pop quiz, what value is contained in the size variable? What is 10 times size of int? All right, so size of int is 4, because int is a 32-bit integer. 32 divided by 4 is 8, which is the size of 1 byte. So this is going to be 4 times 10 is 40 bytes, is going to be the size of 10 integers. So if we call ftruncate on this file descriptor that we just got, let's find out what that does. Man ftruncate. So ftruncate truncates a file to a specified length. It's going to take a file descriptor and a length. Now, truncate normally implies that we're going to shorten the file, but this says it truncates it to a size of precisely length bytes, so that necessarily means that it's going to change the size, whether that will make it shorter or longer. Now, if the file was previously larger than this size, the extra data is lost. That's what we would expect from truncate. But if the file previously was shorter, it's extended, and the extended part reads as null bytes, so we're going to fill it with zeros. In the representation of integers, that'll mean 0 integers. That's not super important, but that's what's happening. Is if the file was created, we're going to create a file that is 40 bytes long of zeros. RVF truncate. Next thing that we're going to do is, today's new trick is we have a system call called mmap. And this is the single most powerful system call we are going to learn about this semester. The single most powerful function we're going to learn about this semester. What this does is it manipulates our page table. This is the way that we get new entries into our page table that are going to map virtual addresses to anything, be it physical addresses or files on disk or whatever we're going to do. And in fact, this is the way that memory allocation is actually primarily implemented on Linux and modern Unix type systems. So sort of anything to do with memory, if we're allocating memory addresses, we do it with this mmap system call. So it's going to take a bunch of arguments. The first argument is address. So that's the address that we are requesting for the virtual address that we're requesting. If we want to allocate a specific virtual address, that might be useful if we were doing something like loading an executable from disk and wanted to put like the data section in a particular location in memory. But for a running program, normally we're just going to pass that in as 0, which tells the operating system that it can pick an unallocated virtual address for us. Length is going to be how big is this allocation. Now, factually, we can only request allocation, or it can only allocate chunks of memory in whole pages. So requesting anything smaller than 4096, or not an even multiple of 4096, isn't terribly useful. The allocation will actually get rounded up to the next page, but we're going to go ahead and put in size and request 40 bytes. We request 40 bytes, we're going to get 4096 bytes, 4K. We want our prot to be prot read, prot write. So we're marking this page of memory that we're allocating as being readable or writable. If we, for example, didn't put in write and then we wrote to that memory, attempts to write to this pointer would result in a seg fault because we were trying to access memory that we didn't have permission to write to. But we're going to go prot read and prot write. There's also a prot execute flag somewhere. Next up, we have a flags thing. Now, flags is a little bit more complicated. Let's go ahead and come down to flags here. So here's the prot argument. We do read, write, exec. We also can say prot none, so we can allocate memory that we aren't allowed to access at all. That's actually useful. For example, the page that is directly below the stack in memory is mapped as prot none in order to cause stack overflows to always result in a seg fault. Alright, so the flags argument gives us some options, and the one that we're interested in is map shared. Now, there's two important options here, map shared and map private. Map private is used for sort of normal memory allocations. If we were implementing malloc, we would want map private. That means that the pages are allocated in such a way that when we fork, those will be copy on write pages and will result in having two separate pages of memory for the two processes. In contrast, map shared means that if this memory is also mapped into another process, both processes are going to be able to access the same page of physical memory. Now, for the purpose of mapping a file into memory, which is what we're doing, if we want the writes that we're making to the file to be visible to other programs ever, we want to say map shared. Because without map shared, when we unmap it, the changes will be lost because a private mapping, any changes we make to that memory only appear in our virtual address space, not anywhere where they would be shared, like a file on disk. All right, next argument here we have file descriptor. We are trying to map a file into memory, so we're going to pass that file descriptor that we allocated, and then offset. If we wanted to map like the middle of a file into memory, we could specify an offset, but we want an offset of 0 because we want to map the beginning of the file into memory. Now, mmap is a system call. Because mmap is a system call, the convention is that mmap is going to return -1 if it fails. Mmap also returns a pointer. Now, -1 is not an especially valid pointer. It would refer to somewhere way high in memory. We saw in the discussion of the Stalker story that high memory tends to be allocated to the operating system, low memory to the program. -1 is the highest possible memory address, so that's not really a valid user memory address anyway. If it were a valid memory address, it would be mapped to the operating system. That's true even on a 64-bit system, even though the operating system mapping is huge. But yeah, if we return -1, it's an error. We have to cast a long to check it because a pointer is conceptually an unsigned integer. Then the next thing that we're going to do is, after we've called mmap and it succeeds, we then have this pointer x's, which points to a location in memory. And because it was mapped to a file and map shared, any data we write to that region of memory will also be written to the file sort of transparently by the operating system's virtual memory mechanism. So we can do something like for int ii 0 to 10, x's ii is ii times ii, and then we'll go ahead and clean up after ourselves. So we allocate, or we map some pages with mmap. When we're done, we free them with munmap. So we'll pass in the pointer and the size. We then have to clean up the fact that we opened a file, so we'll do a close system call on that file descriptor. Close actually can fail. It will return -1 if it fails. If close fails, you have something weird going on, but those weird things do sometimes come up. A good example is network file systems frequently will fail on close as they try to like sync something across the network that they had lied and told you was a successful write earlier. So there's our program. Now we can say that it compiled. We can see in this directory we have an executable called saveArray. We have a file called savearray.c. We run saveArray, and now we have a new file called array.map. If we count how many bytes, we discover that that is a 40-byte file. That makes sense. We truncated that file to a length of 40. And then if we open it up in Vim, we'll find the contents of that file, which don't look terribly useful. But if we know the way Vim displays binary files, we can cipher out what's going on here. So this caret @ sign is the way that Vim is going to display a null byte. So that's a 0 byte right here. So we have 1, 2, 3, 4 0 bytes in a row. Integers are 4 bytes. 4 0 bytes in a row as an integer is the number 0. For loop index 0, 0 times 0 is 0, so we expect the first integer in the array to be a 0. The next 4 bytes are caret A. Caret stands for control in this case, so control capital A, null, null, null. Now, amusingly, the display, or the way that control characters are represented, that's when you hold down the control key on a keyboard and then press a key, is as low ASCII characters. So the ASCII code 1 is used to represent the thing that you get if you press Control A on the keyboard. And so Vim is displaying a 1 byte as Control A here in its display. So Control A is 1, Control B is 2, Control C is 3, Control D is 4. So what we have are the bytes 1, 0, 0, 0. You'll remember that because Intel architectures are little endian, we get the least significant byte first. So the most significant bytes are 0, least significant byte is 1. This integer is a 1. 1 times 1 is 1. Next we're expecting a 4. That D is A, B, C, D, so Control D is 4. Then we have a tab. I think ASCII 9 is tab. Then we have Control P, we could count, we're expecting it to be 16. Control Y, we're expecting to be 24. Z is 25. This feels off by 1. No, 5 times 5 is 25. Y is 25, Z is 26. Makes sense. And then we start to have bigger characters, but it's plausible that this data content is our output. But to be sure, we're going to have to write a program that actually reads this back in. So let's go ahead and copy saveArray.c to print array.c. So print array is going to be just like save array. We need our assert OK. We're going to go ahead and we're going to work with an array of 40 bytes. Our open is going to be different. We never create a file, we never truncate a file. We're going to open a file just for reading. So we don't need to specify well, we're going to open it for reading and writing, but we're going to require that it already be there. We're going to call open and expect to have that succeed. Since we're requiring that the file already be there, we're not going to worry about truncating it. It's already the right size. We're then going to map that file into memory at a location that we're going to name x's, and the mapping is the same. We're mapping 40 bytes, read-write, shared. If we make any writes to the file, they'll be visible to other programs. We're going to use our file descriptor, 0 offset. Mmap, not ftruncate. We're going to loop through, and instead of filling in the array, we're going to print out the contents of the array. Then we're going to unmap and close. Print array.c. RV was not declared. Go ahead and declare that. Now it compiles. We run print array, and we're going to print out the first 10 integer squares correctly. And you can see here that nowhere in this program are we calculating those squares, so we must be getting them by reading them from the file by using mmap to do file IO. So that's what mmap does. It allows us to manipulate our page tables. One thing that we can do with mmap is do file IO through pointers. This has some trade-offs. Maybe there's a performance advantage. Maybe there are convenience advantages in programming to be able to have the data in memory representing something be the same as the data on disk representing something, with no sort of serialization step translating between those two things. But storing data in files is one thing that we can do with mmap. There's a bunch of other things that we can do with mmap, and we'll see several of them as the class goes on.